So in our previous video, we introduced the dot product, and in this video, we want to talk about the geometric ramifications of a dot product calculation. So to start here, what we're going to look at is we're going to look at a way to define an angle between two vectors. So if we have two vectors, either in 2D or 3D, in this case, we're obviously dealing with an x, a y, and a z axis. So these are three-dimensional vectors. We define theta to be the smallest angle that's between those two vectors, right? So there's more than one angle. I've got really infinitely many ways to place an angle between these. I can come down here. I can kind of come out of the screen toward you and define the angle that way. Theta is going to be defined to be the smallest such angle between the two vectors. Vectors that travel the same direction is going to have a theta value of 0. Vectors that travel opposite directions are going to have a theta value of pi. And then if the vectors are perpendicular, and this might be a new word, orthogonal. So whenever we have this word, orthogonal, being used in place of the word perpendicular, most of the time it's due to the fact that there would be infinitely many ways for two vectors to be orthogonal to each other, right? If I assume that this is a 90-degree angle right here, oops. If I assume that what I was trying to show right there is a 90-degree angle, I can kind of pivot vector B around on this intersection point and have infinitely many ways to maintain that 90-degree angle. So whenever you have many ways to be defining something that's perpendicular to, in this case, another vector, we usually use the term orthogonal rather than perpendicular. It shows that there's many ways to be having that 90-degree angle arise as opposed to just several. And then, of course, we see the value here for perpendicular vectors is going to be pi by 2 radians or 90 degrees. In calculus, we'll typically be sticking with radians. This is just kind of a brief review. We're not going to really get too involved with the law of cosines here, but this is something that's necessary to understand in order to see how the dot product calculation relates to the angle that we were talking about on the previous screen. So the law of cosines is something that you would have developed in a pre-calculus or a trigonometry class that is essentially the Pythagorean theorem if you don't look at what we have subtracted off at the end, right? We have a squared equals b squared plus c squared. So it's basically what you would see for the Pythagorean theorem. But because we're not necessarily applying this to a right triangle, we have this extra little fudge factor that's subtracted off here at the end. The way that you relate the sides and the angles is that the angle is defined with a capital letter, and then the side opposite of that angle is defined with the corresponding lowercase letter. So the sides are defined with the lowercase letters, and the sides and angles that correspond to one another are opposite from each other. And you can define, any version of the law of cosines that you want. One that involves angle A, one that involves angle B, one that involves angle C. So the reason why I have this triangle inverted and not necessarily the way that it's most convenient for us to look at it is because I wanted you to be able to relate the law of cosines to this figure here. So this figure obviously corresponds to that figure that we were just looking at. We've got vector A in blue here. We've got vector B in red. And then this vector that's in black is actually the difference of vector A and vector B. So the angle that's between, the smallest angle that's between vector A and vector B is defined to be theta. So we see theta here. What I'm going to do is I'm going to basically apply the version of the law of cosines from the prior screen to this triangle right here. So I'm going to involve the angle theta, right? So if you notice how those worked, whatever side is being squared, isolated on the one side of the equal sign from the law of cosines, you have the angle that corresponds to that side, or the angle opposite that side, popping up in the cosine ratio at the end of each of those versions of the law of cosines. So I have the side, or the magnitude of the vector A minus B, and then I have cosine of theta at the tail end of that, and then what I have for the remaining portion of the right-hand side is I have the magnitude of vector A squared, magnitude of vector B squared, and then minus 2 magnitude of A, magnitude of B. And that is just a direct application of, I guess it is this bottom version of the law of cosines with the appropriate replacements being made, right? Magnitude of a squared, magnitude of b squared, magnitude of a, magnitude of b, and then we had the difference of a and b squared here for the magnitude, and then we had that angle theta in that position. So let's think about this left-hand side of the equation that we established from the law of cosines on the top of the screen. If I have magnitude of a minus b, what I'm going to do is I'm going to compute the x component of that difference vector with just subtracting the x components of the individual vectors, subtract the y components of the individual vectors to compute the y component of the difference vector, and then the same thing with the z component. Well, if I'm doing a magnitude calculation, I'm going to be squaring each of those differences, and then I'm going to be taking a square root after those squares are summed in order to turn it into a magnitude calculation. That's a direct application of our three-dimensional distance formula, essentially. Now, we don't just have the magnitude of vector A minus vector B here, we have that being squared. The nice thing about squaring both sides of this top line that you see I've written out is that the square root goes away on the right-hand side, and that right-hand side gets much, much nicer. We have the opportunity to do quite a bit of algebra here. I can't distribute this exponent in, but what I can do is I can FOIL out each of these expressions in order to generate a much bigger expression. If I FOIL out a1 minus b1 times a1 minus b1, this is the result that you're going to get, and you're going to get the same result with different subscripts for FOILing this out and for FOILing this out. So what I wanted to do is just kind of rearrange a little bit. So if I grouped my a1 squared, my a2 squared that I would get after FOILing out this expression here, and my a3 squared, I'm just going to kind of put that into its own little set of parentheses. I'm going to do the same thing with the b1, the b2, and the b3 that are all squared, right? Just kind of rearranging and grouping. And then I'm going to have these pieces at the end. So they're all going to have minus 2s for the coefficients. And then I'm going to have a1, b1. I'm going to have another one that has a2, b2, and then another one that has a3, b3. If I factor out that common coefficient of negative 2, then I just have a1, b1, a2, b2, a3, b3 summed inside that last set of parentheses. What you hopefully notice about what is right here is that this is the dot product calculation. So let's try to develop some sort of a relationship between this dot product calculation and what we actually started with at the top of the screen, which was essentially a law of cosines problem. Notice that this right here is, if I put a square root over that initial set of parentheses, this would be the magnitude of vector A. Because the square root's not there, that's really the magnitude of vector A squared. Similarly, if I put a square root over this second set of parentheses, the one with the b's inside, I would have the magnitude of b. Well, that square root's not there, so this is the magnitude of b squared. So this is magnitude of a squared. Right here we have magnitude of b squared. We have this coefficient of minus 2. What we have in this set of parentheses, we already argued, is a dot product calculation. So what from this version of the law of cosines is the dot product going in place of? Well, the dot product is going in place of the magnitude of vector A times the magnitude of vector B times cosine of the angle that's between the vectors. So this derivation that we just did was to basically develop this theorem. So if I have a dot product between two vectors, that's going to always be equal to what we saw the dot product had replaced from that version of the law of cosines that we were dealing with throughout the previous screen, which is a dot b is equivalent to the magnitude of vector A times the magnitude of vector B times cosine of the angle that's between them. So this gives us a way to determine angles between vectors with a pretty simple sequence of calculations that doesn't really involve us doing any real heavy-duty drawing of the vectors, measuring with protractors or anything like that. So just to kind of wrap up this video with a quick example, I left this one blank. This is the two-dimensional version of one of these problems. We'll look at the three-dimensional version. So we want to compute the angle that's between the vectors. So we have an x component of 1, a y component of 3, and a z component of negative 2 for vector A, x component of 2, the j is missing, so y component of 0, and then a z component of negative 3 for vector B. If I do the dot product calculation between vector A and vector B, multiply the x components, multiply the y components, multiply the z components, sum the results, what we end up with is we end up with positive 8. If I take the magnitude of vector A, I'm going to get square root of 14. If I take the magnitude of vector B, I'm going to get the square root of 13. So why did I do these three fairly simple calculations? Well, think about what this result from this theorem said. If I have the dot product calculation between two vectors, that's always going to equal the magnitude of the first times the magnitude of the second times cosine of theta, which is the angle that's between those vectors. So if I take these results and plug them into that theorem, I've got the dot product equal to the magnitude of the first times the magnitude of the second times cosine of the angle between the vectors. Well, if I wanted to solve this, I'm going to have to isolate the cosine ratio first. So divide the 8 by square root of 14 times square root of 13. And then if I want to know what theta is, I'm going to have to do an inverse cosine calculation to both sides of this equation to get this value for theta. Obviously, I didn't toss that into the calculator or anything. It's not a real nice result that we get in this case, but this is the angle that's the smallest one between the two vectors that were defined on this screen. So we're going to do one more video within this little introduction to the dot product, and it's going to involve two calculations called the component and the projection of one vector onto another.